Okay, so today we're going to talk about limit properties and different properties of limits that can help you solve for them. And these are really important to go over before we go over analytical methods of finding limits or using algebra to find them. So first we're going to go over some basic limits that everyone should know. So the first one is when the limit of x approaches c and your function is just some constant number, so in other words some b number, your limit is always equal to b. So this is the case when you're taking the limit of a horizontal line. So when you're taking the limit of a constant number, the limit is just the constant number itself. The next thing that's important to be aware of is that the limit as x approaches c for x is just equal to c. So we can just plug the c in for x and that'll be our answer. And that segues right into this one, the limit as x approaches c for x to the n, where n is some integer power, so like 2, 3, 4, whatever. That is the same thing as above. You're just going to plug the c in, but we just have to remember to keep the power with it. So the limit for that one is going to be c raised to the nth power. So now we're going to go over the 5 real big properties of limits. And for this one, we're going to let the limit as x approaches c, some function f of x, be equal to L, and the limit as x approaches c for another function g of x be equal to k. So our first property deals with it's called a scalar multiple property. So it's when you multiply a function by a constant number. So the limit of x approaching c for some constant b times the function f of x is the same thing as pulling the b outside of the function. So since the b is a constant, we'll just pull it outside and deal with it at the end. So we get b times the limit as x approaches c for f of x, and that's just going to be equal to b times L. So really you just multiply the constant by the limit at the end. Our second limit property deals with the sum and difference of different functions. So when we take the limit of x approaching c and we do f and then either plus or minus, so either add or subtract g of x to it, we can distribute that limit sign over the two functions, and our final answer is just going to be L plus or minus k. So we're just going to have the limit of the two separate functions, and you can add or subtract them together, depending on whatever sign was in the middle to begin with. So since we already did addition and subtraction, now we're going to look at a third operation between functions, and that's when we multiply them together. So in the case of when we have the limit of x approaches c for f of x times g of x, and just like in number 2, when we just plugged in the L and the K and then put the appropriate operation between them, going to be the same thing here. We're going to have L times K for our final answer. So when you have the product of two functions, the limit is just going to be the product of their two individual limits. Okay. So our fourth function, since we already covered the 3 main operations, we're going to cover the fourth, or division. So when we have the limit as x approaches c for some function f of x divided by another function g of x, just like before, we're just going to plug the limits in appropriately. So instead, our answer is going to be L divided by k. But now we just have to be careful and put on this extra condition where k cannot equal 0. And that's because if we had a 0 in the bottom of our fraction, we'd get an undefined answer. We don't really like undefined in math, so we're just going to ignore that case and make sure it doesn't happen. And then our fifth property that we're going to go over is called the power property. So if we have the limit as x approaches c of some function f of x, and we raise that function to a power n, all the limit is going to be the limit of the inside raised to the power. So we're just going to get L to the n. And so on the next slide, we're going to go over an example to show you how you can use those 5 properties to split apart functions and make your life a little easier by dealing with smaller chunks. So for this, we're going to do the limit as x approaches 2 of a polynomial function 4x squared plus 3. So our first step here is going to use property number 2, that sum and difference property, to split apart the 4x squared and the 3. So we're going to rewrite this as 4x squared, the limit of 4x squared, plus the limit of 3. Okay. And so now the 4 in the first term is a constant or a scalar multiple, so we're just going to pull it outside and deal with the limit of x squared and then multiply the 4 back in at the end. So we're going to have 4 times the limit as x approaches 2 of x squared. And then instead of writing the limit of x approaches 2 of 3 again, we're going to think back to those basic limits we talked about at the beginning, and 3 is a constant, so the limit as x approaches 2 of 3 is always going to be 3. So we'll just write the 3 there instead. We're going to make sure that we put parentheses around here so we realize that we're not again taking the limit of the 3. Okay, so now we can think back to those basic limits again since we have x squared, and we can just plug the 2 in for x. So we're going to get our limit is 4 times 2 squared plus 3. And so if we follow order of operations and simplify, we're going to get 4 times 4 plus 3. So our final answer when we simplify is going to be 19. So we'll just write that up there to get our final answer, and that's all you do. So just like any other function, you can split it apart using those limit properties and break it into smaller chunks to work with. And this is a great example that's going to segue into our next topic of limits of polynomials. So as you can see up here, 4x squared plus 3, that's a polynomial. And if you were to plug in the 2 from the get-go, you would have gotten the same answer of 19. So we're going to talk about that next. So for the limits of polynomials is any just string of x to a power added or subtracted to each other, and they can have different coefficients. Our limit is just going to be equal to the y value of the function. So if f of x is a polynomial, the limit as x approaches c for f of x is just going to be equal to f of c. So all you have to do is plug in your x value and you'll have your limit. It's going to be the same as the y value at that x value. Okay. So an example of that would have been what we just did with the 4x squared plus 3. If you plugged in the 2 for your c value from the get-go, you would have gotten the 19 just as quickly. So the important thing to remember from this is that the limit of polynomials are just equal to the function value. So now we're going to talk about the limit of rational functions. And rational functions is just the division of two polynomials. So if we have a rational function r of x, we could really rewrite it as f of x divided by g of x. So a rational function is a fraction that has variables in the bottom and possibly in the top as well. So it could be written like that. So if we take the limit of a rational function, or the limit as x approaches some value c for r of x, we can really rewrite that as the limit as x approaches c of f of x over g of x. And just like before, when we plugged in our c value into the polynomials, we're going to do the same thing here. So the answer here is going to be f of c over g of c. But just like on that page where we talked about the limit properties, this is only true as long as g of c does not equal 0, because we want to make sure our answer is defined. So we don't want to have a 0 in the bottom of our fraction and make it undefined. Okay, so an example for you here would be if we take the limit as x approaches 1 of x squared plus x plus 2 over x plus 1. So if we do a quick check and plug that c of equaling 1 into the bottom, we can see that we're not going to get a 0, so we can just go ahead and plug in. So when we plug in, we're going to get 1 squared plus 1 plus 2 over 1 plus 1. Simplifying and following order of operations, we're going to get 4 over 2, which simplifies down to 2. So that would have been our final answer. So the next type of limit we're going to talk about is limits involving roots. And we're going to talk about limits with nth roots. So that's any root. It could be square root, cube root, taking the fourth root of something, any root you want to. So these are going to be for limits of the form like this, where we have limit as x approaching c with an nth root of x, which, just as a review, you can rewrite that as the limit as x approaches c for x to the 1 over n power. So rewriting that nth root as a fractional exponent. And so, just like before where we've been plugging in c, the answer is going to be equal to c to the 1 over n following certain conditions. So the first condition is that this is true for all c values when n is odd, so when taking the odd root power. And that's because when you have an odd root, like a cube root, you can take the cube root of both positive and negative numbers, so you don't have to put a restriction on what your c is. But this is only true for c that are greater than 0 or for positive numbers when n is even. And so our example there would be, think of square roots. You can't take the square root of a negative number, so it wouldn't be true here if you had c being -1 and our example being a square root. It wouldn't work out for you. So that's one thing to just be careful of. And next we're going to talk about the composition of limits, or the limits for the composition of functions. And so this is a little bit trickier to set up, but it's actually pretty simple. So all this is if we have two functions, f of x and g of x, and they follow these conditions. So in math we're going to use the word such that with the abbreviation st, so if f of x and g of x are functions such that the limit as x approaches c for g of x is equal to L, and then the limit as x approaches L for f of x is just going to be equal to f of L. Then we have this really important result. So then the limit as x approaches c of the composition of these two functions, or f of g of x, is just going to be the same thing as taking f and moving that limit inside, so f of the limit as x approaches c of g of x, which is just going to be equal to f of L. So pretty straightforward. It just means that you can move that limit inside to work with the inside function first and then plug into the outside function to get your final answer. So to show you how that works, I'm going to do an example problem. So here we're going to do the limit as x approaches to the square root of x squared plus 4. So in this example, our c value is equal to 2. G of x is going to be equal to x squared plus 4, or that inside function. And we're going to let f of x be equal to just the square root function, or the square root of x. Okay. So now if we look at this, if we do the limit as x approaches 2 of g of x, we can just plug in, because g of x is a polynomial, so we get 2 squared plus 4, or 4 plus 4, which is equal to 8. And then we can go back up to our original problem and rewrite it to look like the composition of functions that we were just looking over. So we get the limit as x approaches 2 of f of g of x, which we just showed was all you want to do is take the limit of g of x and then plug that into the function. So our limit of g of x was 8, so our final answer is just going to be equal to f of 8, which is equal to the square root of 8. And now, in math, we like to simplify things as much as we can, so we're going to simplify that square root, and we can do that by pulling a 4 out of it and making it 2 square root of 2. So that's going to be our final answer there. So that was an overview of your limit properties that are really important for you to know, and next time we're going to look at how to solve limits analytically and manipulate functions using algebra to figure out the correct answers. Okay, have a great day.